Hi guys, in this video we'll continue with the elimination handout. We'll pick up here with section F. That is, when either substitution or elimination is possible, which reaction will occur? At this point we're going to start sort of looking back at substitution and sort of comparing it to elimination. And again, asking which reaction will occur in a given, with given reagents or under given conditions. Okay, the first statement we can make is heat typically favors elimination. And this is due to entropy. If you take this alkyl halide in water, heated in water, it's very likely to give the E1 product, especially with higher heat. And we can envision forming HBr. And actually water here, if you look at it, if we just show HBr, it really plays no role. Ultimately, this is just an elimination reaction where if you heat this compound, it eliminates HBr and we form the alkene. We form the Zaitsev product, yeah? Okay, this is an E1. You should know why it's an E1 and not E2. If we ignore the water, we see that one molecule is converted to two. And thus this is an increase in entropy. Now if you remember our Gibbs free energy equation, we recall that temperature magnifies the entropy term. And if your entropy term is favorable, as it is in this reaction, if you raise the heat, you're going to be magnifying a favorable term. And that drives the reaction to an elimination. If we did a substitution reaction, we would be going from, say, 2 molecules to 2 molecules if you look at a substitution. For example, here, if we take this same alkyl halide and heat it in water, we could envision an SN1 substitution to give the alcohol plus HBr. But this is 2 molecules being converted to 2. And so entropy is not favorable here. Thus temperature is really not magnifying anything. Ultimately, temperature tends to favor elimination reactions. Now you got to be careful. Many substitution reactions require heat. We're not saying that any heat produces elimination. What we're saying is that more heat tends to favor elimination. Okay, we can see examples of this. Number 2, when either substitution or elimination is possible, which will occur? Well, if we have involvement of a good nucleophile, this will favor substitution, while poor nucleophiles will typically favor elimination. If you take this alcohol, react it with HBr, we're most likely to get a substitution product, SN1 in this case, That's because the nucleophile here, Br minus, is a pretty decent nucleophile. Okay. Now, if we react this alcohol with HF instead, we're more likely to get elimination because F minus is a more poor nucleophile, a worse nucleophile. Now, in both cases, in both of these unimolecular mechanisms, the carbocation is the intermediate. The difference is, with substitution, the bromide attacks the carbocation and gives the substitution product. That's because bromide is a better nucleophile. F minus is a worse nucleophile, and instead what it will do is it will act as a base, okay? It's actually a better base. And acting as a base means it takes an H, electrons move in, and that gives ultimately elimination, not a substitution product. Now, alcohols are routinely eliminated. We can eliminate water, we can dehydrate them to the alkene, okay, using sulfuric acid. It's a very common reaction of alcohols, and this would be an E1 mechanism. That's because there is no good nucleophile here. As we said back when we were doing alkene chemistry, we said that the bisulfate anion will never act as a nucleophile. And so we can protonate the alcohol, leaving group can leave, and we can get our carbocation. All right, a couple of steps there. There's no nucleophile. But something will act as a base. Anything can act as a base. We can use this or water. Okay? By the way, water's present here. Sulfuric acid is an aqueous acid. Now, water could actually act as a nucleophile. But if water added here, we'd be going backwards. Okay? We need to lose water to form the carbocation. The only other nucleophile is bisulfate. It will never act as a nucleophile in this class. It's a poor nucleophile. Okay? But either one of these can take an H. Water can do it, or I usually again show the conjugate base here. Take the H, these electrons move here. And that will give your alkene. Again, elimination takes place because there is no good or strong nucleophile here. If we try to do the same reaction, same type of reaction with HI instead, okay, protonate, water leaves, we make the same carbocation, I minus would actually add to the carbocation to give a substitution product. Because I minus is a pretty good nucleophile. We talked about nucleophiles back in the substitution handout. Explain why alcohols cannot be dehydrated by an E2 mechanism. Well, I'll let you think about that on your own. It's pretty darn straightforward. You cannot eliminate an alcohol by an E2. Okay, it's going to be E1. Okay. Here's a mechanism you can work on. It's actually a dehydration mechanism. We make that plus water. Water is eliminated from this molecule. You can give that mechanism a try. Remember, when you're doing carbocation chemistry, carbocations are prone to rearranging. We also have resonance often of carbocations. And so that's some of that is likely what's going on here. So a good mechanism for practice there. Number three, under when trying to determine if substitution or elimination will occur. Well, a more sterically hindered base will favor elimination over substitution. We've actually already stated this a couple of times. All right. This substrate here can undergo substitution or elimination. If we wanted to eliminate, which base down here would be best? Well, the answer is the more sterically hindered base. Tert butoxide is one of the most common sterically hindered bases. Sodium or potassium tert butoxide. That's because the steric hindrance, it's hard to get in here and do a backside attack. You see these methyl groups, they look small over here. They're a little bit bigger than they seem when we draw them. And it leads to steric hindrance. This is also a secondary halide. So instead of it coming here and substituting, it's more likely for the strong base to take the beta hydrogen, electrons move in and kick off the leaving group. And so you'd want to use the more sterically hindered base if you wanted to get elimination. Where if we used, I'm sorry, I drew in, that's an H there. Shouldn't have drawn it in. If we use something like hydroxide, we're more likely to get substitution than if we had used T-butoxide. Because hydroxide can just come in here, do backside attack. I won't draw in that H there, and we can just substitute. And so here, a sterically hindered base is going to more likely give you elimination than substitution. Now ammonia would be also likely to give substitution. No sterics there. If you wanted an amine to do sterically hindered, to be sterically hindered, remember triethylamine. Triethylamine is an amine that can be used for, why did I say E1 here? That's E2. Thank you. I heard you say that. E2. If we wanted to use an amine to do our E2 elimination, triethylamine would be a good choice. Sterically hindered amine. Okay, so there were three different sort of things to consider when we're trying to decide between substitution or elimination. Before we move on, we can also add that with sterically hindered bases in E2, we also have the idea of Zaitsev versus Hoffman. And if the base is very sterically hindered, we're going to start getting more preference for the Hoffman elimination. But in the example given, there is no regiochemistry with our elimination. The only elimination we can do is the one shown. Okay, a couple of miscellaneous topics to finish out this handout. One is clever ways to make ionization of an alkyl halide to the carbocation easier or faster. Okay, such as in your SN1 or E1 mechanisms. And the first is the use of a Lewis acid to activate the halide. Now we've used Bronsted-Lowry proton acids to activate OH groups, make them better leaving groups. But halides we've never activated. They really don't need to be activated. Not usually. But sometimes they could use a little help. We do not protonate halides, but one clever thing we can do is react them with a Lewis acid, and one of the most common is silver ion. And we have silver plus here. Silver nitrate is a common source of the silver ion, and the halide will actually complex with the silver and now the bromine is positive. Okay? Typically this does not take place with proton. But some metal ions halides will complex with. Now if you remember from your Gen Chem solubility rules, silver halides are not soluble in water. That's because the bonding between silver and a halogen is very strong. And that's sort of what's going on here. The bonding will also occur between a neutral halide and the silver ion. At this point, this bromine is now positive. It would really like to get its electrons back. Instead of taking them back from silver, it takes them from carbon and leaves the carbon. And that gives our carbocation plus silver bromide. And these two, which really love each other, have bonded together. And this is lots of water. This is going to actually precipitate. Show it here. Because silver bromide is not soluble, and that actually helps drive the reaction to the right as well. So if you're having a little trouble with your reaction rate and the halide is thus apparently not ionizing quickly enough, one clever trick is to throw in some silver nitrate and envision this mechanism to help your halide ionize off after it complexed with the silver. You will get silver bromide precipitate. Then we can get our reaction here. Something takes the H, water can take it, or we could actually use the nitrate anion. It's a rather complex ion. These electrons take the H, these electrons here. That would give nitric acid. All right. And as shown, water didn't even participate in the reaction. Or we could use water to take it. If you use water to take it, you would end up, of course, with H3O plus and the NO3 minus. Of course, that's how nitric acid exists anyway in water. So again, this is similar to how proton acid makes OH a better leaving group down here. We can use a proton acid, get the same product. Here an OH is a leaving group, proton acid to protonate it, and get the E1 product here. Okay. Now silver ion is also used as a chemical test for the presence of ionizable halogen. Okay? I mean, the same thing. If you think that this is your unknown compound, you know, you come across an unknown, okay, you think it's this, you could just treat this with some silver nitrate. All right? We're not worrying about what chemistry we're going to do here. We're not worrying about making an alkene or anything. What we want to say is, do we get silver bromide precipitate, which is going to be a white precipitate? Okay? We would expect a white precipitate with this compound because this chemistry is going to take place. It's going to form silver bromide white precipitate. And the observation of this positive result would give us more evidence that this may be our product or our unknown. The halide has to be ionizable. It has to be able to leave. Okay, here when this leaves, we get a secondary carbocation. Question, which compounds below would give a positive silver nitrate test? All right. You can pause the camera and think about that. Pause the video, think about that. Well, these three would give positive. This would give a negative. Okay. No matter if you complex this with silver ion or not, this bromine is not going to leave because it is not on a tetrahedral carbon. It is on a trigonal planar sp2 carbon. All right. Leaving groups do not just up and leave when they are on trigonal planar sp2 carbons. Even if you protonate the OH or even if you complex them with silver ion. All right. This is a tetrahedral carbon, secondary carbocation. All right. These three, the halide is all on a tetrahedral carbon. Question, of these three, which will give the precipitate of silver bromide the fastest? Well, this is just asking which carbocation is going to be most stable and thus most readily formed, and it will be that one there, because it's going to form a tertiary / secondary carbocation. Where over here, this would give a secondary carbocation. It would be isolated, no resonance. And this one here would give a primary slash secondary there. Which would be the slowest? Well, it would be this one, yeah? But all three would give, now I say slowest, it would probably still be within a minute or two. It's not going to be slow. I mean, all three of these are going to give a positive test. But if we had to rank them, if we were asked to rank them, that would be fastest, then that one, and then this would be slowest. Okay, number 2, which is another clever way to make ionization faster, and that is use a polar solvent. If you take this alkyl halide with this alcohol and heat it in a polar non-nucleophilic solvent such as acetonitrile or DMSO, we can get this substitution product where the alcohol, okay, it used to be a bromine bonded to that carbon. Now the alcohol, the oxygen is now bonded to the carbon, and we lose the H to the bromide, make HBr here. All right, so we just did an SN1. With the weak nucleophile. You want to do this in some solvent. Choice of solvent. You want to use a polar solvent. Acetonitrile, that is CH3CN. CH3 carboxylic acid is called acetic acid. This is the nitrile of acetic acid. It's called acetonitrile. It was probably on the solvent list I gave you back during test 1. DMSO is very similar to acetone, except it has a sulfoxide dimethyl sulfoxide where acetone would have a carbon here. It's a carbonyl instead. Both of these are considered polar. They are polar. They're also non-nucleophilic. That is, they will never act as a nucleophile. I have to cringe when I say that. I have seen acetonitrile act as a nucleophile, but it's kind of rare. So non is like when something's deionized, it still contains ions, yeah? Non-nucleophilic, okay. Let's call them less nucleophilic. The difference is something like ethanol which is a common solvent. Ethanol, it can be a nucleophile. Just like in this mechanism, well, what is the mechanism? This, we get the carbocation, all right, and then this nucleophile attacks. Well, if you did this reaction in ethanol, you're going to have a competing nucleophile. I mean, they're just the same. They're both alcohols. We don't want our solvent to react. We want this reagent to react. Well, if you use acetonitrile DMSO, they will not react here. The alcohol is much more nucleophilic compared to those two. Of course, it's a weak nucleophile, but these two are almost not nucleophiles. All right, let's don't belabor that much. But they are considered non-nucleophilic solvents, but they're polar. Okay, if you try to do this reaction in hexane, all right, nonpolar, it's probably not going to react at all. No reaction. Because the first step is leaving group leaving. Make ions. But ionization is not favored in nonpolar solvents. Okay? I mean, in Gen Chem, you learned that if you put ACl in water, a polar solvent, you are going to get ionization. Okay, and it's actually going to become ions. All right, and of course mechanistically the water actually takes the H, stays here. So this is not just leaving group leaving, but we did form ions. If you put HCl in hexanes, you learn that HCl remains covalent. It does not ionize. There are no ions formed. Now, there's slightly different considerations going on here, but in the end, polar solvent promotes formation of ions. Non-polar solvent, things are going to prefer to stay covalent. Okay? Ions and hexanes don't love each other. So, if we want to do carbocation chemistry, we typically want to use a polar solvent to promote ionization to the carbocation. Okay. Next miscellaneous topic. Let's look at the deuterium isotope effect. This is a neat way to determine if an elimination reaction is going to be E1 or E2. Look at this reaction. If we take this alkyl halide and heat it with pyridine, okay, and we could envision an elimination reaction taking place, okay? Or we do this and indeed we get this product and thus we know an elimination reaction has taken place. We next may want to know, is the reaction E1 or E2? Well, at this point we know that strong bases will operate by E2 mechanism. And if we do not have a strong base, the mechanism is going to be E1. So is pyridine a strong base? Now it's kind of borderline. Something like triethylamine, an sp3 hybridized nitrogen, we called a strong base. Pyridine, strong or weak? You could make an argument, but that would be just a theoretical argument. What type of evidence could we look to get to prove if the mechanism is E1 or E2? First off, we could consider rate information. We could repeat this reaction using double the concentration of pyridine and see if the rate changes. All right. What if we double the reaction of the concentration of pyridine and the rate doubles? That means that pyridine is involved in the rate determining step, and that means the reaction would be indeed E2. Now, if we double the concentration of pyridine and the rate remained the same, that would tell us that pyridine must not be involved in the rate determining step, and thus the reaction is E1. Now, another way to answer this question is to explore the deuterium isotope effect. And in this case, we can repeat the reaction with the substrate that has a deuterium in place of the beta hydrogen. Now, this is not necessarily easy. You would have to find or even make the compound with the deuterium here instead. That's not going to be trivial. Perhaps it's commercially available. Okay. So that is one drawback here. But assuming that we can get this molecule with a deuterium here in place of the beta hydrogen, then we can explore the deuterium isotope effect. Now, if removal of the beta deuterium now, or beta hydrogen, if that's part of the rate determining step, then the rate of the reaction with the deuterated substrate will be slower because the CD bond is stronger than the CH bond. And if the rate is slower, KH over KD will be greater than 1. That means the rate with the H will be faster. So that's a higher number divided by a lower number. That's going to be greater than 1. So the rate with the deuterium deuterated compound is slower. Now, which mechanism is removing the beta hydrogen part of the rate determining step? All right, that would be E2. All right, if we did an E2, we would take this, electrons move here, okay, E2, all right. I'm showing an E2 here. Deuterium is removed. It's all one step, yeah, concerted beta elimination, E2. But you see in this mechanism, the D carbon bond is being broke. All right. Now remember, this D carbon bond is stronger than the H carbon bond. because this bond is stronger, this is going to be more difficult than if it was an H. And if we're doing an E2, that reaction's thus going to be slower. All right. If we're doing an E1, the deuterium, of course, is not removed in the rate determining step. And so we would have no deuterium isotope effect. And thus KH over KD equals 1. That is, they're the same. Okay, there's several things going on. I took us kind of around there. You can straighten all that out. Basically, is the CD bond broken in the rate determining step or not? Those are your two mechanisms. If it's broken in the rate determining step, that reaction rate is going to be slower because the CD bond is stronger than a CH bond. It's actually about, well, it's stronger. It's a mass effect. We're getting into a lot of deep theory of bonding there. The mass of a deuterium is significantly greater than the mass of a proton. Okay, some homework here. Provide both the substitution and elimination product for each of the following reactions. And then below, last topic of this handout is double E2 elimination. Okay. I'll let you look at that. I'm going to end this video here. Please do homework there, see what type of questions you have as we pull this all together. Okay, guys.